Okay, in order to demonstrate this standard, I have the question here from the book. Is the space to the right of the y-axis in figure 29.28, which is below, contains a uniform magnetic field of unknown magnitude that points in the positive z direction. As a conducting square loop placed in the xy plane oriented with its horizontal and vertical sides parallel to the x and y axes is moved to the right across the y-axis at a constant speed of 2 meters per second. A 0.24 volt EMF is induced in the loop. A. If the side length of the loop is 0.3 meters, what is the magnitude of the magnetic field? And B, what is the direction of the induced current in the loop? So first of all, I just wrote down a few of the equations we'll be using here, and then I just wrote down a bit of a key for what they mean there. So first of all, what I'm going to do is I'm going to replace this here with this equation. So I'll do that down below. So it'll be E induced equals negative D times BA over DT. So that'll give us that, and then now we can actually take the B out of this, making it, come on. Sorry, it's freezing because of the picture. Come on, there we go. So now we have this is B times D over dt. So that is just including this here into that equation. So now we have that simplified, but now we have this one over here that we can plug in for this A. So this is just further simplifying it into terms that we can use for this equation. So now we have B times dlx over dt. And so once again, we can take L out of the equation here and bring it over here. And then we get BL dx over dt. So now we have more variables that we can actually use. And then now we can say that dx over dt is actually equal to v. So this is something else that we can place into this to further simplify it. So now we have BLV. So now for the overall equation, after we have again and again simplified, we can say we have E induced, oopsies, is equal to BLV. Now that we have that, and since we are searching for B, which B is the magnetic field, that we can rearrange the equation for that. So we can say B equals to, what would it be? No, it would be E induced over? Yeah. E induced over LV. That'll just give us the final equation that we're going to use. So now we can substitute our values. So first of all, for V, we have, if we look above, is 0.24 volts. And then it says, where is it? Right here, the side length, which is going to be L. So L is equal to 0.3 meters. And then, oops, I went with wrong thing. I saw the V in the EMF and instantly with that, so this is actually induced here. And then V itself is going to be the velocity here, which is 2.0 meters per second. So now we can calculate B, which is 0.24 volts over 0.3 meters times 2.0 meters per second. So if I could plug that in my calculator real quick, 0.24 divided by 0.3 divided by 2, it's going to give us 0.4, and I think maybe volts divided by meter divided by meters per second, that's going to give us Tesla. So this is going to give us the magnitude here of the magnetic field. So now we need to figure out what is the direction of the induced current. So since we know that the magnetic field is in the positive z direction, I believe that says it right here. Unknown magnetic field that points in the positive z direction. And then we just found, where is it? I'm sorry, lost my train of thought. That the flux is increasing here. So then that would mean, I think that means the loop is opposite. Right?